Okay, I think we'll start with that, and then those who are joining midway are more than welcome to join. So, I welcome you all to this live session on problem solving for the engineering mechanics course. Before we begin, I'd like to introduce myself to those who have not been attending the past sessions. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics, working under the guidance of Professor K. Ramesh. And my co-guide is Professor U. Saravanan from the Civil Engineering Department. So, just to brief, the idea behind this live session is to solve some problems, live problems, and then answer the doubts that students get. So, I would urge you all to, solve the questions along with me, so that wherever you have a doubt, we'll discuss and get it clarified. And also midway, I'll perhaps maybe we can have a Google poll on some questions so that it is a little interactive and I'm also able to gauge what has been understood clearly and to what extent. So those who are not aware, there is a forum in the Swayam portal where if you press ask a question, there is a tab. You'll be able to see that it's a Google forum where you can join and get your doubts clarified. So over and above this session, if you have any questions, you are more than welcome to ask them there and we'll clarify that. Okay, with that, I suppose we can get started. The topic of discussion today is virtual work principles. So before that, are there any questions what we discussed last week or previous week before that? That is trusses or beams. If there are any, I'm happy to take them now. Otherwise, we will move on to virtual work. So, are there any questions there? So we had developed for zero force member identification, and then we had discussed bending moment diagram and shear force diagram. So I hope those are clear. Okay, so with that, let us start. So first thing we need to keep in mind is that work. What exactly is work? Work we get from dot product, and so work is a scalar. So F cross R, or rather R cross F, I should say correctly. Moment is R cross F, as we have seen, right? And force, work is given by force dot some displacement, U, corresponding displacement. If you see, the units for both these are Newton meter in the SI units. So this should not be confusing to anyone that work is a vector or a scalar. Work is indeed coming from the dot product, which gives you a scalar. So one needs to keep this in mind, that work is a scalar. Now, what is virtual work? But similarly, as we can see, that work is force dotted with displacement. Virtual work is either virtual force dotted with a real displacement, or it can also be construed as virtual work is force dotted with a virtual displacement. So what are the difference between these two? Here we basically deal with displacements as the unknown quantities, and here in this we deal with forces. Yes, someone has raised a hand. Yes, please. Yeah, who has raised a hand? Could you please ask your question? Yeah, Vishnu, I'm not able to hear you. Instead, Vishnu, could you consider typing it out in the chat box, because I'm not able to hear you. I think there is some audio issue. Okay, while you type, just so basically, the second equation is when forces are the unknowns, and the first equation we use when displacements are the unknowns. So in our study, mostly in engineering mechanics as of now, we will be dealing only with forces as the unknowns. So this is the equation that we will be using the most. So same thing I have translated it to a symbolism as given. So work, if it is given by W, we just put a delta there in order to signify that it is virtual work. So that is what it is. So as we have seen that work is force dotted with displacement. Similarly, work can also be construed as moment dotted with a rotation. Okay, so as we have seen in a generalized force system, we can apply either a force or we can apply a moment or both put together. So in the case when both are put together, since it is scalar, we can simply add it. So the total virtual work can be defined as the dot product of force with the virtual displacement and moment with the virtual rotation is what it is. But in general, we don't go ahead and separate them out. We just say a generalized force system. A generalized force system means it could have moment as well as forces. All these come under a generalized force system category. Okay. So from the lecture, if we see why do we use virtual work, this method, when we have already solved so many problems with the equilibrium of rigid bodies, why is it that we need virtual work principles? So this is basically helpful for analyzing interconnected rigid bodies, systems where there are more than one rigid bodies, where there are deformable bodies involved, for example springs. All these systems cannot be analyzed simply with the methods of equilibrium that we have seen. So virtual work is nothing but an alternate method to analyze equilibrium of systems. And these system virtual work basically extends our scope of the problems that we can solve as compared to the normal force equilibrium that we have been seeing so far. But there are certain things to be kept in mind while using virtual work principle. So the system we need to introduce, as we have seen, virtual work, this is the equation which we will be using. As we have seen that virtual work is force dotted with the virtual displacement. Invariably we will be giving virtual displacements which are parallel to those forces. So this dot product, what is a dot product? We saw that dot product of two vectors is AB cos theta. So when theta is 0, that is we will make the both parallel, the virtual displacement parallel to the force, theta becomes 0, so cos theta becomes 1. So we generally take it to be a product, but it is a dot product is something one should clearly understand. uh, Okay, so virtual displacement we need to introduce, but there are certain conditions with which we can introduce them. The virtual displacement can be arbitrary, infinitesimal, and it has to be consistent with the constraints of the system. What these are, what these words mean, I will explain in the subsequent slide, but one needs to keep this in mind. Okay, so forces dotted with the virtual displacement, corresponding virtual displacement is what give us virtual work. Okay, so another thing that needs to be kept in mind is if there is a force, if there be a force like that, let us say this is F, and then it traverses a distance, this is the virtual displacement. Let us say it doesn't actually traverse, it is just an idealization we make. So it is to be kept in mind, if the force is in the direction of the virtual displacement, then its contribution, the virtual work contribution, is to be taken as positive. And if it is in the opposite sense, let us say that this were pointing towards the left. If this was pointing towards the left, then the virtual work contribution would be negative. This can easily be seen by considering it to be a dot product, because when both force and virtual displacement is in the opposite direction, theta becomes 180. So cos theta becomes -1. So that is the negative work, virtual work contribution. That is what is to be kept in mind. So what exactly is the principle of virtual work? It states that a mechanical system is in equilibrium if the virtual work done is either negative or zero. So the virtual work done by the system is either negative or zero for every virtual displacement that we have given. Negative basically comes with when we deal with frictional forces, but as of now we will be considering systems without any friction. So basically we will say that virtual work, we will equate it to 0 in order to analyze the system. This quantity will have some unknown forces and we have an equation to solve it. So with that, we will be able to solve for the unknown forces is the key concept here. So what is arbitrary, consistent and infinitesimal virtual displacement? Arbitrary is, we can, for example, if we have a joint here and we want to rotate this, we can either, let this be theta. So we can either rotate it such that theta increases, or we can rotate it such that theta decreases. So this choice of increase or decrease is left to us. So that is what this arbitrary is meaning to say. Consistent with the constraints of the system. Let us take this example on the right side. So we have seen that for a beam which has a hinge and a roller over here and a roller over here, it offers reaction. If we were to draw the free body diagram, we have seen that it offers reaction like that. Okay. But this is only the case when a downward force is there. If we were to apply a force, for example, in the opposite direction, such that this beam lifts off, there is loss of contact here. The thing would just stay here. The roller just stays there, and the beam simply lifts off. In which case there is loss of contact. So this is not a case of consistent virtual consistent virtual displacement, which we are supposed to give. That is, the displacements that we introduce into the system should respect the constraints that are there, and it should not lose contact with anything because of the fact that we have introduced the virtual displacement. This is something to be seen. So if we see this example, there is a roller that is supported by this wall B, and we have introduced a virtual rotation such that the contact is lost. So this is not to be considered as a case of consistent virtual displacement. It is not consistent with the constraints of the system. What are the constraints of the system? The roller support offers a reaction like that when there is a force like that. So this is what is to be seen. And infinitesimal, of course, these are not real displacements that we are giving. As professor also explains in the class, that in the lecture videos, if you see that if there is a ladder, before climbing the ladder, we just tend to shake it a little, not physically shake it, but just to give it a little feel whether it is stable or not. We are actually introducing a virtual displacement. This is something we'll be doing mathematically. That is all the differences. So the virtual displacement has to be consistent with the constraints we have applied to the system. Okay. And the forces which contribute to virtual work are called active forces. The forces which do not contribute to virtual work, given if there is a system and we introduce a virtual displacement, and there are some forces which do not contribute to virtual work. When could that be? We have seen that this is force dotted with virtual displacement. So when does this dot product go to zero? When the force and the virtual displacement are perpendicular. So if we see in this case, only those forces which actually have a non-zero virtual work contribution are called active forces. So that is something to be kept in mind. So if we see here, if we just see this question, how many generalized active forces are present in this system, as shown, that contribute to virtual work due to a consistent virtual displacement given. What would be an inconsistent case here? That we apply a virtual displacement that basically leads to loss of contact here. So that is a virtual displacement that is not allowed. And the constraint, we have already mentioned that it is the question already says that the virtual displacement that has been given to the system is consistent with the constraints of the system. And which are the forces that will contribute to its virtual work? So we can see that there will be a reactive force here. There will be a reactive force here. Three reactions will be there, and then there is a force applied here. So we have to visualize what are the virtual displacement that we can give this system. We can either, it could either go like that. That is, this distance could increase. If we call this D. I am not allowed to lift this point up. This is not allowed. So it can only traverse along the horizontal plane. This is a constraint we have already got. So how can it traverse? Either let this angle be theta. Either theta could increase or theta could decrease. Right, write a little more clearly. Theta could decrease. So these are the only two ways we can introduce virtual displacements into the system. In such a case, which are the forces that will actually contribute to the virtual work? We can see that these are the forces which actually would, and if we consider these reaction forces, see this is hinged at A, if we can see the constraint. So there is no movement at A. So virtual work contribution of the reactions applied at this point, call it A. The virtual work contribution of the reactions applied at that point are zero. So these do not constitute active forces. Likewise, we have introduced a constraint, we have introduced a virtual displacement in this direction. So this is perpendicular, this force, this reaction force is perpendicular to that. So cos theta becomes, cos 90 is 0. So there is no contribution here. Likewise, this is just a force applied in the opposite direction. This also does not have a contribution. So basically we have a contribution only from these three. So we have only three active forces here. Why this is necessary? When we look at a system, we should be able to identify what are the active forces in that system which will actually contribute to virtual work. This way we can write the virtual work equation with less number of unknowns and not introduce redundant quantities which are not actually required there. This is the idea behind that. Okay. Coming to one more concept called the degrees of freedom and how to identify them. So basically this deals with in order to identify a total configuration of system, we need to identify some parameters with which we can define that system. For example, if we were to have a single case of this link, and if I were to take horizontal as my datum, and if I just rotate it by some angle, I'm able to define where each and every point would lie in that link. In which case, I require only one theta, only one parameter to define the entire configuration of this system. So that is what is called the degree of freedom. Based on the degree of variation in the degree of freedom, the total energy that the system has or the total potential to do work that the system has would change. And the change is what we are trying to analyze in this virtual work concept. Okay. Having said that, if we were to consider this system, how many degrees of freedom does this system have is the question. If we are to analyze that, first what we would do is we'll consider this first member. Let us say this is 1, this is 2, this is 3. If we have to consider this first system, just the first link which is hinged over there, this consistent with this link can only rotate either this way or that way. So it has only one degree of freedom. Call it theta. Let us say this is theta 1. So either theta 1 can decrease or theta 1 can increase, but it can only rotate about that point. It cannot translate because it is fixed to the hinge. So this has 1 degree of freedom. Now we'll attach the next. Now we'll go ahead and attach the next link to that and fix this entire, whatever we have analyzed, those we will fix. So what are the things that we are fixing here? We are fixing the hinge and we are fixing this first member. And just look at the second member. How can it rotate about the first member? It can rotate with some theta 2. Again, theta 2 can increase or decrease. So this theta 2 becomes an additional information that we need to provide in order to understand where each and every point of system links 1 and 2 lie. So this again has 1 degree of freedom. And likewise, by similar arguments, we can see once we fix this entire thing, this entire system we fix, and just look at the third link, that will have another theta 3 with respect to this. So that also has 1 degree of freedom. So if we were to count it out, there are a total of 3 degrees of freedom for this system. So this is how we are supposed to analyze for degrees of freedom. Anyway, this would be taught in detail in higher orders, higher subjects. When we go into design of machinery and theory of machines, this is dealt with in more detail. But since it was touched upon in the lecture, I thought that it should be just explained a little bit at least. Okay, now let us come to the application part of the principle of virtual work. We've seen whatever has to be contained and has to be looked into while applying the principle of virtual. We have seen. Let us look at one example. So this problem says that given that this P is 285 newtons is given and B is given to be 4 meters. So this length of this link is 4 meters. That is given. And this theta is given to be 120 degrees. So what is the value of this Q? What is the value of this force Q in Newton that is required to maintain the system in equilibrium such that theta is maintained at 120 degrees? We are supposed to maintain this at equilibrium such that theta is 120, considering all these to be massless. So the assumption behind that is that we are not including the gravitational force of contribution in the virtual work, because otherwise these also will be having weight which will actually do some work. That is not something we are looking at right now, so that is why we have been told that the links are massless and there is no friction in any of the joints, so that is also to be ignored now as of now. Okay, the first thing that we need to do here is to draw the deformed configuration, to at least visualize it. So that is something that is required when we analyze systems like this. We can easily see from the very construction of the system that when we apply force P, if this Q wasn't there, this joint would go away. So it would be something like that. So our deformed configuration would look something to that effect. Of course, this will be parallel, but I hope you get the idea that this is something we need to visualize. So we can see that when we apply, let us say this is also theta from the construction. Let us say we apply P such that theta decreases, in which case we can see that this distance, if we call this D, we can see that from the deformed configuration that D would increase because of this deformation. And we have a force Q that is applied in the opposite direction to that. So from this we can conclude that the virtual work contribution of Q when we apply a virtual displacement such that theta decreases, we can see that P would do positive virtual work, Q would do negative virtual work when theta decreases. So this, I hope that is clear. Now coming to the geometrical constraints, we can see that if I just erase this, if we join this line and call it H, so we can see that if this is theta, then this is theta by 2. So what will H come out to be? This is given to be 2b. This length is given to be 2b. So we can see that H is 2b sine theta by 2. Okay. So from symmetry of the problem, we can see that each P will affect only H. The bottom P will affect this bottom H. Like that. Okay. So now that we have got h, let us also calculate d. What will d come out to be? If this is h, what will this distance be? Let us call this d1, d2, let this be d3. Is d1 plus d2 plus d3. d1 we can see it is 2b cos theta by 2. And from the system we can see that d1 is equal to d2. So we just need to multiply this by 2 plus what is d3? What is d3? It is again b cos theta by 2 into 2. B cos theta is still here, so that into 2 is d3. So it is nothing but 2b cos theta by 2. So from here we are able to see that in total d comes out to be 6 6b cos theta by 2. Okay, so now we have got h as 2b sin theta by 2 and d we have got as 6b cos theta by 2. Now we have the relations. Now we need to calculate, we basically need to give the system some virtual displacement. How we'll do that? If we give the, we just differentiate it with respect to the coordinate, that is the independent coordinate, the degree of freedom that is there. So we just differentiate this equation. What is the differentiation of sine theta? It is cos theta, and then differentiation of theta by 2 will come out to be 1 by 2. So this comes out as b cos, sorry, delta theta by 2, theta by 2 into delta theta. So one thing we need to keep in mind is, unless and until we write the principle of virtual work equation relating all the unknown forces, we are only allowed to consider the absolute values of these. We shouldn't assign the sign as of now. We should only assign the sign when we write the principle of virtual work. Till then these remain as absolute values. Okay, similarly d is 6b cos theta by 2. Now if I were to differentiate this, we'll get 6b comes outside, so it will be 6b minus 6b sine theta by 2 into delta theta by 2 is what we'll get. But we should remember that we should always take the positive absolute contribution of this. So it will be 3b sine theta by 2 delta theta is absolute value of delta d. This is absolute value of delta h. Okay. Now from the system, what are the active forces we have identified? This is one active force. Again, another P is applied. This is another active force. And then we have the third active force here. So there are in total 3 active forces. So we have to account for the virtual work contribution of each of the active force. We have already seen that P contributes a positive virtual work, whereas the contribution of Q is negative. So P, this is a positive contribution. And then we have another P which will also do positive virtual work, and this is again positive. And then we have a negative contribution from Q, which will be negative. These are the forces that we need to account for, and this is the principle of virtual work. We have just written the principle of virtual work. So we have accounted for all the active forces. We have considered only the magnitudes, only the absolute values of the virtual displacement, and these signs, sine to virtual work assigned based on physics of the problem. This is something to be kept in mind, otherwise we'll never reach the correct answer. If we simply see that d has a cos theta and we differentiate that and we get a minus sign and we carry that over to the end without applying our mind, so we won't be getting the correct answer. It is to be essentially understood that which are the active forces which do positive virtual work and which are the ones that do negative contribution to the virtual work, and accordingly put their sign while writing the principle of virtual work. So this just if I were to substitute this, I'll get 2p delta h. Delta h we have already got here. It is b cos theta by 2 delta theta minus q into delta d. Absolute value of delta d is 3b sin theta by 2 delta theta equal to 0. From here we can solve. D cancels out, this cancels out, and we get 2p by 3q as tan theta by 2. And already we have been given in the question that theta is 120. Here we have been given theta as 120, p is 285 and b is 4. Although it is interesting to note that in our final equation b doesn't show up. So what does that mean? That the system's configuration, the ratio in which p and q change, does not depend on b. So even if you were to assemble a member which has longer arms, let us say if we were to change b and have a member, shrink it, scale it down or scale it up, the ratio in which p and q change, the p and q change doesn't get affected. That is the message we are trying to get from here. Okay, so if we were to substitute, q comes out to be 2 into 285 upon tan 60 by 3. So q comes out as 109.7 newtons. So this tells us that for this configuration, if two forces of 285 are applied like that, and we have to maintain this theta at 120 degrees, then Q which should be applied has to have a magnitude of 109 newtons. So this is what the problem tells us by solving it by virtual work. So are there any questions at this point? If there are any questions on how we have solved, I'll be happy to take them. So you can consider it posting in the chat box also. If there are no questions, then we'll move further to the next part. Okay, I take it that there are no questions. So we'll just move on to the next problem, which actually we'll be able to appreciate the principle of virtual work better when we deal with systems with springs. So, so I just included one problem from that as well. Okay, before we start this problem, there is something we need to understand. A spring is an element which offers resistance to deformation. If we were to pull this, then the force that develops in the spring would be opposite to the direction of the pull. If we were to push this instead and make it short, then it would offer a force. This is the spring force. The spring would offer a force that opposes this motion. So it invariably contributes. The message here is that the virtual work contribution of a spring is invariably negative. If we pull it, it develops a force which tries to bring it back to its original position. So it is negative. because cos theta is 180, theta is 180, cos theta becomes minus 1. So force Fs dotted with delta U becomes negative for a spring invariably, even if you push it or pull it. So that is something we need to keep in mind up right from the beginning, so that we don't mess up with the signs while solving this problem. So a straight rod is connected to a linear spring. This is the linear spring of spring constant K at end A, and we have this connected at D, and then we have a link. So this rod is pivoted at B. So we'll be able to see that when we apply a force downward like this gets stretched. So the rod is pivoted over the pin support and is free to rotate about B. About this point, it can freely rotate. The rod can freely rotate. And it is further given that the spring is unstretched when the rod is horizontal. That is, when theta equal to 0, spring force is 0. That is, at this unstretched condition, the spring doesn't offer any force. It only offers a force when it is deformed, either elongated or contracted. So this will help, and we have to ignore the mass of the assembly. So this rod which we are seeing, we have to consider this. We have to ignore the mass of that rod as of now for solving the problem. So we are only looking at how many active forces. One active force is the spring force, and the other active force is P. So we are looking at only two active forces as of now. For this, if we were to draw the original configuration, this is B. We have been given that this is B. This is 1.2 B. And then we have a hinge here. This is again pivoted here. So this is given as B. If we see here, this has been given as B. This is the original configuration when when the spring is not stretched. That is what is said. So length of the original spring is, from geometry we can see that this is 90 degree. This is B. This is also B. So it is nothing but B root 2. This is the original length of the spring. Now elongated length of the spring is something we need to calculate. Why? Because elongated length minus the original length will give the net elongation in the spring. Spring force is nothing but the stiffness into net elongation. This D is net elongation in the spring. So for this, we invariably need to calculate what the net elongation is. So that also we can do from geometry. If we were to consider this diagram itself, we can see that this is B, this is given. What will this angle come out to be? This angle is nothing but theta plus 90. The horizontal makes the angle 90, and then we have theta. So this becomes theta plus 90. So if I were to draw the deformed configuration again, it looks something like that. This is 90 plus theta. This again we have a spring here. And then this is B, this is also B. So from here, if we draw a perpendicular line, we are able to see this angle. This angle would be 90 plus theta by 2. Why? Because B, both are same. So it divides the angle also into two equal halves. So this angle is nothing but theta plus 90 plus theta by 2. It comes out to be 45 plus theta by 2. So I may as well write it here straight away. I'll take it, this is 45 plus theta by 2. So now if I just consider this triangle, if I just consider that triangle, I'm able to see what is this length. Let this length be A. So I'm able to say that A is nothing but B sine 45, sorry about that, 45 plus theta by 2. This we are able to see clearly from the geometry of the problem. So what is L elongation? Elongated length, we can see it is nothing but 2A, because this has divided both, it's an isosceles triangle, so it has divided it into two. So if we double it, we will get the total length of the stretched spring, which comes out to 2A, which is nothing but 2B sine 45 plus theta by 2. Okay, now let us calculate the spring force. We have got L elongation as 2B sine theta, 2B sine 45 plus theta by 2. And then we have the original length of the spring to be B root 2. So what is the elongation? Is final length minus original length. So it is 2B sine 45 plus theta by 2 minus B root 2. I hope that is clear. So if we can answer the first question, which of the following options, there could be more than one, correctly represents the net elongation of the spring in terms of B? So we have just calculated that the net elongation is 2B sine 45 plus theta by 2 minus B root 2. 2B sine 45 plus theta by 2 minus B root 2. So we can see that D is one option. D is the correct option that we are sure of. But now, since the question says there could be more than one option correct, we can just analyze the rest of the options. Rest of the options, we can see they are in terms of either sine or cos. So this definitely cannot be an answer because D is an answer. We can conclude on that. Now another two options which could be viable choices are in terms of cos theta. So we can just think what relates cos theta and sin theta. So we know that cos of 90 minus theta is sin theta, or rather let me not use theta too much, so as to avoid confusion. Cos of 90 cos of 90 minus alpha is sin alpha. This is a identity that we all know. So here alpha is nothing but this is alpha. So in terms of cos, what will it come out to be? 90 minus alpha. Alpha is 45 and then minus cancels out. So this comes out to be cos of 45 minus theta by 2. So the message here is sine of 45 plus theta by 2 is same as cos of 45 minus theta by 2. Do we have any option such as 45 minus theta by 2 minus b root 2? We can see that A also represents the same thing in terms of the same angle but a different uh, cosine. It is using cosine instead of sine. So we can see that these two are the correct choices that we can make. So what have we calculated till now? We have calculated the net elongation in the spring, and we know that force in the spring, we have seen it is nothing but the net elongation scaled by a constant which is called the spring constant into the net elongation which we saw. So we can easily calculate this. This will be nothing but 2kb sine 45 plus theta by 2 minus kb root 2. I just multiplied it by b. Okay, that is all. So we have got the spring force. Now what other active forces do we need to check for? This P is an active force. So we need to apply a virtual displacement such that P moves. So since the coordinate is this, if we were to extend this and get this height, what will H come out to be? From the figure we can see that from this figure, we just extend this and name this as H. So H comes out to be 1.2 B sine theta. Since this is theta, this is also theta. From this triangle, we can easily see that H is nothing but 1.2 sine theta. Okay. So if we were to give it a virtual displacement, what will this come out to be? It will be 1.2 b cos theta delta theta. And we are always to consider the absolute value till we write the principle of virtual work. That is something to be kept in mind. Likewise, we have got the elongation. If we have to write the principle of virtual work now, we know that, let us say that theta increases. Say theta increases. So P will do a positive virtual work, we can see. So this contribution will be positive. And irrespective of theta increasing or decreasing, we know that the spring force will always do a negative virtual work. Because if theta were to decrease, still the spring would be contributing negatively because the spring force always opposes the applied displacement. Minus spring force into delta net elongation. That is what it is, equal to 0. Now we know this P is something that is one unknown. That's fine. Delta H we have already calculated in terms of theta over here. Spring force we just calculated here. We just calculated spring force in terms of theta and K here. This we have not yet calculated. We have just calculated D. D came out to be the total elongation. This is D. This is our D. So if we have to calculate delta D, we know it will be 2B cos 45 plus theta by 2 into delta theta by 2. And the contribution of B by root 2 will be 0 because it doesn't have any theta term. So I'm just writing just for clarity in case there is any confusion. And we are supposed to consider only the absolute value as we have seen. So this 2 and this 2 will get cancelled. It will be B cos 45 plus theta by 2 delta theta. So we have got all the components that we need to write the principle of virtual work now. So let us go ahead and write it. Plus P into delta H. Delta H we have got 1.2 B cos theta delta theta. 1.2 B minus the spring force we have got as this big quantity. It will be into, this is minus, into absolute value of delta D. So let us calculate this first because it's a long expression. I don't want to go too long. So I'll just calculate that first. So calculated separately, it will be minus 2 kb sine 45 plus theta by 2 minus k. I won't take this minus as of now. I'm just calculating this, okay, it will be minus kb root 2 into delta d. We got it as d cos, this is delta d. You just have to multiply this out. So what will this come out to be? 2k p squared sine 45 plus theta by 2 cos 45 plus theta by 2, and then minus kb squared root 2 into cos delta theta, of course, cos 45 plus theta by 2 delta theta. This is what we will get when we multiply it out. So we know one relation, that 2 cos alpha sine alpha is sine 2 alpha. This we know. So if we apply this, we'll be able to see, we'll be able to simplify this. We have a 2 here, we have sine theta cos theta, so it will be kb squared into sine 2 alpha. Alpha is 45 plus theta by 2, and let the rest of the thing be as it is. So I won't write it again. Let me just copy and paste this here. It will just come here. We'll just have that term there. So if we multiply this out, what will this come out to be? Kb squared sine, we take the 2 inside, it is 90 plus theta. 90 plus theta minus kb squared root 2 cos 45 plus theta by 2. And the entire thing is having a delta theta. That is understood. Now we know that sine of 90 plus theta is cos theta. So a little bit of trigonometry is required. Trigonometric basics need to be brushed up for this. So we have kb squared cos theta minus kb squared root 2 cos of 45 plus theta by 2 whole multiplied by delta theta. This is what this right side, this entire thing comes out to be. So now if I write this entire thing again, so I can just go ahead and erase this and write out what we have got, the simplified version of it. It is minus kb squared cos theta minus root 2 cos 45 plus theta by 2 delta theta equal to 0. This is our principle of virtual work. We have written our principle of virtual work completely. So the only thing that remains is to solve for the unknown. What is the question now? The question is, which is the equation in terms of b, k, p, theta, all the terms that we already have, that this system must satisfy for the assembly to be in equilibrium. So principle of virtual work states that when the virtual work contribution of all the active forces in the system sums up to 0, then the system can be said to be in equilibrium. So we have written all the things and we have equated to 0. So we just need to bring this to a tangible equation in order to compare with our solution here. So we can see that in our answers, all p, k and b have been grouped together and theta terms have been taken to the right. So we'll try to simplify that in the similar manner. So we can see that 1.2 pb upon kb squared comes out as, if I were to take this to the right side, it will be cos theta minus root 2 cos of 45 plus theta by 2, and then delta theta I cancel out everywhere, so that is not required, and then I have a cos theta here. So this again I can take to the we divide the other side by that, so I get 1.2 b t b upon kb squared is cos theta minus root 2 cos of 45 plus theta by 2. For ease of calculation, one could also call 45 plus theta by 2 as some alpha beta and then go ahead and solve, so as to not write it time and again. But since I didn't do that from the beginning, I'm just writing it down like that. So 1.2 is nothing but 6 by 5. We know that. P by kb, because 1b cancels out, comes out to, if we were to take this, 1 minus root 2 cos 45 plus theta by 2 whole by, not whole, only the right side term, by cos theta. So do we have this somewhere in the answer? We see 6 by 5. We know that the ratio is 6 by 5. So this cannot be an answer. That much we are sure. This 1 minus root 2. Yes. So we have this as one answer. And similarly, we can see sine minus theta. Okay. So we can see that we have got the answer which matches here. Okay. So what is the equation? Pb by 5kb equal to 1 minus root 2 cos 45 plus theta by 2 cos theta. This is the equation which tells us what the equilibrium position will be. Where this will be used, essentially, we have looked at how to solve it, that's fine. But we must also understand where this will be used. For example, this is some kind of machine, some kind of component in one machine that someone is designing. And we know what is the weight we'll suspend. Let us say we know P. And then we know the length of these members. And we want this theta not to exceed, say, 60 degrees. Let us say that is a constraint. So we have to select an appropriate spring stiffness. We have to select an appropriate spring such that when we apply this known weight at this point C, our system will come to equilibrium when theta reaches 60 degrees. So this is what this equation helps us identify that. So if we are given a P, if we are given B, and then if we want some to constrain it to some angle theta, we know what is the spring stiffness we should select. So that is the application part of this. So when we design some components or machines, combination of components with springs, what is the spring stiffness we should choose such that we want the desired results is something principle of virtual work empowers us to do. So let's look at the last sub question also. We have got the equation which actually gives us, which defines the equilibrium of the system. Now the assembly attained equilibrium when the angle theta measured 64 degrees. It is given that at 64 degrees, this system had attained an equilibrium. So what must have been the magnitude of force P? What must have been this P applied at point C that caused this system to come to equilibrium? When it was known that the spring that was put, that had a spring stiffness of 25 Newton meter and the length of the member was 0.35. So it is just a matter of substitution. We can see readily from from this question that how it will be applied. If P was not given, P is supposed to be calculated here. Instead, if we know P, if we have to select a spring, again it's just a same problem with one unknown. So let us go ahead and calculate P. So P comes out to be nothing but 5 kb by 6 into this whole big thing, cos theta. And theta we have got as 64 degrees. So 64 plus 45 cos of 64 to 5 by 6 into k into 0.35. So we get that exactly as 2. The answer comes out to be 2 followed by 4 zeros and some decimals. But answer comes out to be 2 Newton. So what this tells us is if we take this setup and we select a spring which has a spring stiffness of 25 Newton meter and let this member length be 0.35 meter and we arrange it in this fashion and then we apply a force of 2 Newton at C, then the system will come to equilibrium. That is, it will just rotate and come to equilibrium when theta reaches 64 degrees. So this is quite an interesting thing to think about if we see that uh, from just one principle, writing one equation, we are able to capture the entire physics of this contraption that we are seeing. So this is the main application of principle of virtual work. Again, this can be thought of from energy perspective also, since we saw that the spring force contribution is always delta D. This is something we saw. If we take it to the right side, we will be able to see that the spring force is nothing but KD, KD delta D is our virtual work contribution of the spring force. Sorry, not delta Fs. It will be delta D. So this can be thought of as the derivative of some potential for conservative systems. The conservative systems are where there is no loss and where you can actually represent the energy at some kind of potential so that you differentiate that potential and get the work. So that is basically explained in detail in the lectures. So I won't delve much into it. But if there are any questions about that, I'm happy to answer them now or perhaps in the next session as well. So that basically says that the first derivative of the potential energy equates to the virtual work done by the external forces. What are the external forces? As we saw, these are the active forces in the system. So this basically requires us not to segregate the system, as basically what we did here was we separated this out and then we applied that Fs here, and we knew that Fs is invariably in the negative direction as the with respect to the applied displacement. So we just calculated and substituted the contribution of the spring force as negative. Instead of separating this out, if we just have to look at the whole system and we know that there is a spring in the system or there is mass, then we can directly represent them as potentials and we can take the derivative of that potential and equate it to the rest of the virtual work. So in our problem, this would only have k component, this would be having p component. We will still be getting the same result. So I encourage everyone to try this out from energy principles. You will get the same answer as we have solved, but just to get the hang that we can approach this problem from different perspectives. So if there are any questions at this juncture, I'd be happy to answer them. Okay, I hope that what we have seen today is clear and you'll be able to approach problems on virtual work principles using the concepts that we have discussed. And should there be any doubt, I encourage you to ask it in the forum and we'll be happy to answer it. Or you can also ask it in the next session that we will be having every Friday for this entire semester. So next week's topic of discussion would be friction. That is the topic for week 6. But it doesn't have to be contained to that. If students or participants have any questions from the discussions of the previous weeks also, they are more than welcome to ask it there and I'll try to answer. Okay, if there is nothing else and no more questions, then this is what I have to say about virtual work. I encourage you all to solve this problem using the energy principles as well. It is nothing but the potential energy of the spring is nothing but, if we see for a linear spring, it comes to half kd squared. D we had got, you just square it and then differentiate it. Delta Vs will be what? It will be kd delta D. This we named as spring force. So it boils down to the same thing. If you see, we just wrote it as spring force. The another way to write it as differential of a potential, spring potential energy. So that is what it is. So I encourage you all to try it out and then ask it in the next class if you have any doubts. Well, if there are no further questions, then I'll call it a day. This is what I had to say about virtual work. I hope to see you all in the next session next week, Friday at 6 on friction. Thank you.